Okay. Now, anyone has solved the other three? Anyone has solved? Not yet? Yeah, it's okay, it's okay. Don't worry. It's not that you need to solve it. No. I just curious if you are solving it or not. Okay. Okay. Yeah, I think we can start the second line here, the left one, because compared with the right, the left one is supposed to be easier. We could start with the U substitutions. Take that. Why I'm taking this? Because when we derive, this is just 2x dx. And 2x dx, if you rearrange this in these substitutions, we can cancel out this 1 over 2x inside this, and we can cancel the x. Right? So I think it is supposed to be obvious, and you need to also be aware. Okay, when you have the integrations, the first thing you can identify is whether this integration can be substituted or not. Whether some component can be substituted, and when you think of substitutions, you need to directly think on, okay, try to derive and see if it's canceling out. When you see any cancellations, then okay, that might be the best way to substitute. Okay? So that's how you identify. So first thing is identification. Okay? At this time, in this process and in this familiarization, so the more you are aware of this, the faster you can solve this problem. Okay? So this will be half, and then this will be square root of u du, right? When we substitute and cancel out. And then we just integrate the u with power of half, then this will be 1 over 2 multiplied 2 over 3. U will be 3 over 2. But we could, let me cancel this. So we could say that this is 1 over 3. U is x squared minus 1 with the power of 3 over 2 plus a constant. Oh, yeah. Oh, okay, thank you. Okay, so I think not really a problem for the left one. Okay, if you are following the substitutions, just a normal substitution. Okay. Okay, if we are going to solve this one, sine x over 1 plus cosine squared, this one here. Anyone solve this? So? No? Well, the best way to learn for substitution, if you don't really know how to identify, because I think if you just follow how the steps and then just how the writing are, my writings, it's not really a solve a problem. The idea for solving all calculus or any mathematics problem is to know the pattern, to know how to identify. First thing, it's the best way to just try. First, maybe 1 plus cos squared. Try to derive. Can we see any cancellation? If not, maybe it's not the best way to substitute. Well, you see, we have sine and cosine. There will be some conditions, right? That there will be some cancellation if we consider the derivative. Well, how about we just take the cosine? Not 1 plus cosine squared, just cosine. If we derive, it's negative sine. We can cancel, right? And then what's supposed to be happening in this equation? 1 plus u squared. What is that? 1 over 1 plus x squared. What is that? What? Yes, the tangent inverse, the Arcus tangent, right? Okay, so I hope that's give you a more idea. So take u as cosine x, okay, and then du. Okay, and then if you think that you need to transform all x into u, then maybe I will also transform the end interval, the interval of the integrations. Okay. So we take when x is 0 from here, then u is cosine 0 is 1. Okay. When x is pi over 2 here, and then u is 0. So from this part, we could say that dx is negative 1 over sine x du, which is cancel with the sine x in the equations. So we will have a negative from 1 to 0, okay, and then 1 over 1 plus u squared du. Well, you could switch the 1 and 0 and then remove the negative. It's okay, right? In integration, that's one property that you can do. But let me just write like this, and let me just compute with this to make things clear. So the integrations, so let me make notes here. That integrations of 1 over 1 plus x squared dx is equal to tangent inverse x. So this will be tangent inverse. So we can take the tangent inverse 0 minus tangent inverse 1. Tangent inverse 0 is just 0. Tangent inverse 1 is pi over 4. So minus pi over 4 minus is positive. So pi over 4. Right? Okay. Or if you want to avoid the negative, as I mentioned, you can switch 0 and 1 and multiply with negative. Okay. Okay, now last question from this 4 is the x and then square root of x minus 1. Maybe zoom here, right? Anyone solve the last one? No? You think you can? Yeah. You can try. idea how to solve the last one here? Usually what the typical substitutions is, we take some substitutions and we derive and we suppose that from that derivative we get the cancellations. But this is not a problem like that. It's a little different problem. From this x and its square root of x, it seems that it has just x, right? Not having any degree. So I'm kind of thinking how to solve this. There's a little bit of trick on how to solve it. But let me show you how, and you will see that this will be one way to solve when you see this kind of behavior. Okay, first, take substitutions. X minus 1. Okay. Why we need to take that? Well, perhaps if we derive it's just du dx, nothing really happens, right? It's still u here, still x here, right? But think clearly, I can rewrite this also in terms of okay. And what we are doing here? So we take this x minus 1 as u. We take x as u plus 1. U plus 1 and then square root of u. U square root is half. You can just multiply each other. You can play nicely, integrate. Okay? So now we take this one. Let me write one step by steps. Okay, so this will be x squared of u, and dx will be du, because when you see this part here, when you derive, this is just dx, and then this will be u plus 1, and then multiply with u with power of half du. Okay, and then u and u power half is just u with power of 3 over 2, and then plus u power half like that. And we can nicely integrate each one, right? So this will be plus 1 is 5 over 2. So 2 over 5, u 5 over 2, plus 3 over 2, so 2 over 3, u 3 over 2. And then what's happened next is we change the u into x, back to the x, so we can write okay, and we can write just like that. Okay, any questions? I think more examples on these substitutions will be will be in the additional video as well. But I think I need to make sure that we can solve this problem. Okay, let me take times to review the fundamental theorem of calculus. Okay, so find the derivative of function. Okay, in the fundamental theorem of calculus, previously I mentioned that we might have a functions that in terms of an integral. Okay, let's say we have see if you still can solve this. And the problem is not just about this, but also because we are still talking the derivative in integration, which means all the things you do, like in the previous chapter, like the sketching curve, concavity, increasing, decreasing. It's also the same problem with our condition here, but the function will be an integral. So the function will be an integral. But the idea is still the same. When you need to find increasing, decreasing, you need just to derive once, and if you want to find the concavity, derive twice, the second derivative. It's still the same. But the difference is the function inside. It has the fundamental theorem of calculus techniques that you need to solve. Okay. Now, if you remember how to solve this, first, basically, what the fundamental theorem of calculus says when we try to derive this whole integration, means that we need to remove this integral symbol, right? Which means that this x power of 4 needs to be put inside. And also by the chain rule, we need to also multiply with the derivative of this x power of 4. Right? So let's do that. So x power of 4 power 2, so it's become 8. Right? So we can write this as cosine x to the power of 8 and then multiply with 4x cubed. Okay. Okay. Now what's happened when we have the let's say g. Let's take another function. This is 1. This is maybe not this one. Maybe x and then 1 and the square root of t plus sine t dt. Okay, so it's asking the first derivative. Okay. How we can solve this second one? Remember, the constant in these integrations will not be any meanings, because at the end the constant will be cancelled out when we prove that, I think, last 2 weeks, right? So whenever constant you put, it doesn't really mean anything. Okay? You just focus on the variables. But now, the variables is down here, translate here. So the first thing you need to do is to
Just put minus.
yes, just put minus and then reverse this x and 1. Like that's the first thing. So 1 x and then this will be minus. Okay, and then do the same thing. We take the derivative, so it means that we are going to take negative x plus sine x. I think we can stop there because I think it's just x, so we can stop here. Okay, another functions that might be a typical problem. So the first problem is just a normal one. Just plug in and then find the chain rule. I think it's not too complicated. Second one, you see the variable down here. We need to switch the variable to here. So that is the well, we say the default of the fundamental theorem. But the other way, or the other problem that might be a typical problem is we have two sides is a variable. Yes, this is the answer. Okay, so how to solve this one? To help you remember what the fundamental theorem of calculus, I think you need to keep this into the default system. Okay, so the default system, if you have f of x, this is, well, f of t, let's say, and then dt. Well, this the derivative is this is, I think, the best way to look at the theorem. So the theorem says that we have a constant in the integration up until some variable x. And then you want to derive this entire derivative. You say this entire derivative. When we want to derive this, which means that the result will be the original function f of x, like the usual f. Right? So our idea within this fundamental theorem of calculus, we need to get into this form, at least a constant and a variable in the integration. And when we look here, we have a variable. Both endpoints have a variable. What we can do is we can separate. Okay, we can separate becomes at least two integrations. Right? So we can separate square x and then maybe constant. Let's take constant in 1 because if you see the domain in these functions, it seems possible to be 1. If 0, I think it's not really possible. So we take 1 as our best choice. So we could take that, and let me write here that we could separate the integrations. The square of x and then 1, and then e power of t over t dt, and then plus 1x. Okay. And now, still, I think the right one here is okay. It's constant, variable. But the left one, again, we need to switch to make it a constant and a variable, okay, to make our fundamental theorems as our default, this structure. So we switch this. Then we can write negative and 1 square root of x okay, and then we can derive each integration. We can derive each one. So we take the derivative. So take derivative, maybe let me write here that dy dx is, or maybe just y prime. Y prime is negative e squared of x squared of x, and then 1 over 2 squared of x, and then plus the other one, e to the x over x. Or we want to take more simplified. Or if you want to make it more, we can combine these two. So this will be 2e power x and then minus e squared of x. And then that will be our answer. Okay, since the fundamental theorem of calculus is related to derivative, you also need to, like, well, it's going to take care of derivative, okay? And all the property in derivative. Also, if you remember that we have the L'Hopital rule, then it's also perhaps some problem related to L'Hopital rule, but the L'Hopital rule will have the integral. So limits something, and then we have the integral. But that means whenever we have 0 over 0, still the same, you can do the derivative on the numerator, derivative on the denominator. Okay? that type of problem might be in our task as well, because it's related to the vulnerability of carbon. I would like to give you another example. Let me give you an example. Okay, let me write a question. So if f is continuous and it's known that the integration from 0 to 2 of f 2 sine theta and then multiply cosine theta d theta no, I think this should be here. So this is actually the questions, and the information is 0 to f of x dx is equal 6. Okay. So then this is the question. See if you can understand, okay, at least understand what this question really asks. The first is, of course, function continuous, and you have the information that the integration of that function from 0 to 2 is 6. Okay, so you have a value 6 here. But you were asked this integration. So integral from 0 to pi over 2 of f, it's not x, but it's 2 sine theta, cosine theta, d theta. Okay. So first, just take time to understand the question. If you would like to try solve, okay, you can try. So the idea of the question is to solve, I think, any problems, like in, especially engineering, any exact course, science course, technological course, blah blah blah, that needs some problem solving. To understand how the question works, is you need to relate what is being asked with your information given. The information is just this, fx dx. Well, we have a different f here, right? It's not x. Okay, that's the problem. So, when we take time to, well, let's say this is our one variable, like any dummy variable, just like in your substitution method. Take time and see what's the relation between those and the information given. Start from there. Okay.
It's actually the same, but this one is also multiplied by
Yes,
cosine
yes,
theta, yeah?
yes,
And
yes.
what is the property for integral when there are multiplication of the functions? Yeah, how we can divide this?
Okay, think like in the substitution method. If you want to substitute in the substitution method, let's say this is u.
Yeah.
This 2 sine theta is u. If you derive, it's become 2 cosine theta. Is that correct? I can cancel it. This can be rewritten as just du. Then you can cancel this. Right? I think. Yeah. Yeah, correct. Okay. So you need to imagine that this 2 sine theta probably plays an important role in our question here. So let this become u. So when we have du, this will be 2 cosine theta d theta. So d theta is 1 over 2 cosine theta. Okay, and then we can rewrite this. And perhaps you want to also change the endpoints. We can do that also. So when theta is 0, u is sine 0, so 0. And when theta is pi over 2, sine theta is 1, so it's become 2. Even when you look at the u, it's 0 and 2. It's the same 0 and 2 with the questions, the information given, right? So we can rewrite this 0, 2, and then f of u. And let me write cosine theta and then multiply with this. So substitute the d theta with 1 over 2 cosine theta du. Cancel this out. And we get that we are having half of integration from 0 to 2 f of u du, which we have in the information that its integration is 6. Okay? So this whole thing is 6. So 6 by 2, 6 divided by 2 is 3. So this is the answer. Okay. Okay, we will take a break. After that, I will give you just an introduction for the next chapter. Okay, the next chapter. And I will give you the results. Okay. So before I give you the score for your midterm, let me just introduce you the next chapter, just like a brief introduction, and then we can have your discussion on your exam. Okay, so the next chapter is we call the application of integrations. Okay. So chapter 6, it's application of integration. Okay. So for chapter 5, okay, some exercise I'm preparing to give you within this week. I hope, if not tonight, maybe tomorrow, I will post in the Moodle. You can have exercise. And probably, if not quiz, maybe a homework that will be done next week about chapter 5. Okay? So chapter 6, this is talking about the application of integration, which means that most of the chapters, most of the section in the chapter 6, we will talk on how to apply integration in more practical problem, which we have discussed a little bit, like the area under the curve, that is actually one of the applications, and also the volume. So we are going to focus on finding the area and finding the volume. If we have like a curve, and then we are going to rotate the curve, and we have like we call that solid of revolutions. That is a solid, it has a volume, and we can actually compute the volume using the integration. Okay. So let's start with the area between curves. So the first part is about area between curves. So to give you more insight what it is, let's say we have this area. Okay. We have two curves, f of x and g of x. We would like to know the area between these two curves. Okay. in the previous chapter 5, we already described that the integration that we have, so it's involved like that, is actually area under the curve of the function inside this integral, right? So if we have the integration of x squared, which means that from certain interval, we are going to evaluate area under the curve of the x squared, for example. And now we can have like a random function, and we have f and g, and we would like to know the area between the curves in between this interval a and b. Okay? Okay, we could take this using the same rectangle that we have done in chapter 5. So let's say we take the sample, let's say that is our rectangle. Let's say we have the delta x here. And then the difference between what we have done, the height, right? The height, usually the height is the function, the f of x. But now we have f of x and then g of x, right? So this height is f of x minus g of x, right? Okay. So the height, so let me write height, or maybe height, this is f of x minus g of x, right? So if we take a sample point, and take the Riemann sum to approach or to approximate the area between these two curves. So the Riemann sum will be the summations and every time I'm writing using the like this kind of like a star or asterisk, this means we take the sample point, so it can be in any point in the area. Okay, so we have this, right? And then we are going to take the same approach as we did in chapter 5. Okay? So we can have a lot of rectangles. And then imagine that when we have the rectangles, like a lot of rectangles, that n is maybe getting over and over and maybe having getting close to infinite number, then we could take the limit, right? We could take the limit, and that is our definition for the integral, right? So that's how we could see this problem. So actually it's quite I think quite simple for the definition. The difference is we are going to take this height as f minus g. Okay, that's the difference. So whenever we have a curve, and then we want to, like we have like two curves, and then it has some intersection and it has some interval. The idea of the area between curves is always, if we take this in y and x like this, it's always the top curve minus the bottom curve. It's always like that. And there's another case when we have, maybe we need to describe the curve in terms of y. Then it's going to be the right minus the left. Okay. But later I will show you. So for now, we know that the area will be a limit of the Riemann sum. Let me just write this for you. Okay. And then we could describe in the definition in terms of integral. So first, the area is bounded by the two curves, f and g. And then also the line x equal x will be like the left side of the curve and the right side of the curve. and then we are sure that the f of x is greater or equal to g of x. Then we could take the area as the integration from a to b, f of x minus g of x dx. So it is important to know which function is the highest one. And somehow, if you maybe you could take examples from the sine and cosine. If you have sine and cosine, sometimes sine will be the top, sometimes it goes down, right? So it's also between intervals. It's also between intervals. So intervals and the equality between these curves will be the key important.
So there must be many integrals for complex.
Yes, yes, yes,
Changing that.
yes, yes. That's also one point. Okay, we could also imagine the structure of the so we could imagine this structure. Or we could imagine this structure. So the integral, not always in the dx, but sometimes we can also describe it in dy or delta y. So for delta x, then we need to make sure we know our curves here and curves here, and yt minus yb multiplied with this delta x. And in integrations, then probably yt minus yb dx. And this one here, describing the delta y. Then we need to find the right one minus the left one. Well, if you think that maybe it's difficult to see like top, down, left, right, but it's actually the same. You could think the left and right, similar to what we have here. You can just think like, maybe you could just see from, like, you can see if it rotates, okay? So if you want to rotate this to the right, then this one becomes right and this is become left. And you can see that you rotate that way, then it becomes this one, right? So still, the same principle, the top minus the bottom one. Okay? Okay, let me give you maybe a couple examples, and we can have early feedback and then deliver your exam. Okay. Okay, let me give you just a description on the example. So find area of region bounded by y equal e to the x and y equal x, and bounded by x equals 0, x equal 1. Okay, so it doesn't give you any specific information on the graph itself. So you need to describe the graph by yourself. And that's also, I think, important to do. So you need to sketch the graph that you need. So if you already know in your mind which one is the highest one, I think you can just put into the equations, still okay. So if you're not sure what the sketch is or how the curve looks like, then maybe drawing is really helpful. drawing the curve is really hard. Y equal x, I think, is a straight line. And e to the x, well, we could check like from 0, 1, 2, and see how it relates to the comparison between the y equal x to y equal e to the x. You can always remember that e is 2.7 something. Okay. So when y is equal 1, so when x equal 1, y equal 1, then this will be y equal e. So e is higher. I think that's already pretty convincing, right? Or when x is 0, when this is 0, the e to the x is 1. So it's already also higher. I think it's also convincing, right? That e to the x is higher than the x. Or if you would like, you could just draw the straight line here. This is y equal x, and maybe e to the x, maybe not like that, maybe here. Okay, and then maybe the 1 is there. Okay. Okay. Now to give you the description of what we need, take a rectangle to imagine the samples of our area. So this one, the x, this one is the height. The height is e to the x minus x, right? That means the area is the integrations. This is x equal 1. Okay. And x equal 0 is, of course, in here. So 0 to 1 is the endpoints. So we're just integrating this. And then plug in 0 and 1. So e minus half minus e over 0 minus 0. So e minus 1 and 1 and half, it's 3 over 2. Right? Okay, while you're writing your notes, let me give you another example. Find area of region enclosed by, well, you could say it's same as bounded by parabolas y equal x squared and y equal 2x minus x squared. So you have two curves, okay? And your question is just asking that. So a typical question in finding the area between curves. Aside like the first one, it's given you all the things you need, like the curves and then the interval. But sometimes they just give you the curve itself, which means that you need to decide the endpoints by yourself. Okay. And to solve that problem, then the first thing we need to do is, aside maybe from sketching the graph, maybe finding the intersections. So we could find the intersection. So x squared equal to x minus x squared. So this will be 2x squared minus 2x equals 0. So we see that this is going to be x equals 0 and x equals 1, the intersection. And then perhaps we draw. I think we can start from the x squared. Let's say that's our x squared. And then to draw the 2x minus x squared, I hope you still can draw that. The easiest one, or maybe the method, is taking the intercept. So taking the intercept is taking when y is equal to 0. So we know that the roots that going to be. So it's going to be 0, and maybe 1 is here, maybe 2 is here. So probably it's going to be around here. It doesn't need to be really precise, as long as it's quite representative for the questions. I think still okay. So this one is the area between the curves. Okay. Now the intersection is 0 and 1. Of course, from 0 we know that this is perfectly there, and this should be 1, right? This should be 1. When x is 1, and y is also 1. Okay, we can conclude that. So we are going to have, let's say, always imagine that there is a sample points here. Take the x and then the height. The height will be the top equations minus the bottom equations. So the area so we can say from 0 to 1, 2x minus x squared minus x squared dx. So we can factor out the constant 2. And then this will be x minus x squared dx. And this will be 2 x squared over 2. And then plug in 0 and 1. So half minus 1 over 3 is 1 over 6, right? 6 by 2, 3, 3 minus 2, yeah. 1 over 6, so 1 over 3. Okay, any questions? Well, actually, I have prepared a feedback function, but I think I will save that for next week. So I will give you the result first, so to see whether you need to take the makeup exam or not. Okay.